next problem will be valid anagram, and we are given two strings, S and T. That's our input. We have to return true if T is an anagram of S and false otherwise. So we'll have a Boolean output. To solve the issue, we first have to understand what an anagram is. And here you have the definition. It's a word or phrase formed by rearranging the letters of different word or phrase, typically using all the original letters exactly once. So if we go to an example, here we have anagram, and I'm not sure how to pronounce nagram or something, but as you can see, all the letters that are contained inside the string S are also contained inside the string T. We have three A's, we have a G, we have an N, and then what's missing? We have an R, Q, and then we have a matching M at the end of the strings. So they are anagrams. The second string is just rearrangement of the first string. On the second example, we have rat and car, and they are not anagrams because the second string is missing T and has an extra C. So they don't have the same letters rearranged. So we just return false. For the constraints, the total length of the strings can vary from 1 and 5 times 10 to the 4th. The thing that's more important is that S and T are consisting only of lowercase English letters. We will see how can we use this back later on to optimize space complexity. But for now, what are our options? First option could be to sort the both strings and then have one pointer that will go through both strings and check if all the letters are the same. So if we have string like this, they are sorted strings. So the initial string could have been like this, and second string could have been like this or something. But after they're sorted, they will be the same. And if we iterate over, we will see that each letter matches the other, so we know that they are anagrams. That's our first option, and the total time complexity would be n log n. But can we do better? So the solution to this problem is to know that the anagrams have the same frequency of letter. So if you have two A's in the first string, you have to have two A's in the second string. So if they match for all the letters that are appearing in S, if we have a match in the frequency count in the string T, we know it's an anagram. It's basically just a rearrangement of the first string. So we can have a hash map that we will go through the first string and count the occurrences of each letter, and the second map to count the occurrences of each letter in the string T, and then we will just compare the two maps and see if they are matching, if they have the same key value pairs. But there might be an easier solution. We can have only one map, and we can see an example how we are going to do that. If we have one map, and also we don't really have to have a map, we can have an array of only 26 elements, because we know that it's only English alphabet. So English lowercase letters. So it's only 26 elements. If we have a letter A, we can basically just match it to the 0 index, and letter B can be matched to the index 1. And you will later see in the solution part how we can do this in Java. But for now, we just assume that each letter in the alphabet matches the index of an array of 26 elements. So if we traverse both strings, this is our string S and this is our string T, and each time for the S string, we will increment the corresponding index for a letter. For example, if we iterate over this string, the first letter will be A. So in this array, we will increase the count for A, and then for N, and then for A again, we will just increase to 2, and so on. But for the letters in T, we will decrement. So we will decrement every time we see an N, we will decrement the value. So in this case, it will go to 0. And once we traverse all the letters, if all the elements of this array are 0 and not negative or positive, that basically means that these strings match. They have the same frequency. Let's see here, for example, we have A, so it will be first A1. We have N, which will be in the second string, which will be now minus 1 because we are decrementing. Then we have N, so this will become 0 because we are incrementing. We have A, so this will go to 0 again. And then we have A again, so this will go to 1. We have G, so it will go to -1 because we're decrementing here. And then we have G here, so this will go to 0. And we have A here, A will go to 0. We have R, which will go to 1. We have R again, which will go to 0 because we have it here. And then we have two A's. So it will first go to 1, and then we will decrement it by 1 because it's appearing in the string T. So it will go to 0 again. And for the letter M, we will first increment it because it appears as the last element of the string S, but then we will immediately decrement it by 1 because it appears as the last letter of the string T. And as you can see, we have all 0 elements. If, for example, we had B here, then the B value will be -1 because it's not appeared here. We haven't increased it ever, so we just decremented once because it appeared in the string T. And also the value for A will not be 0 because we have a missing A here. So we don't have a pair. We cannot like increment, decrement, so it converges to 0. It will be different than 0. It will be -1 or +1 or something, depending on where the extra A is. Is it on the string S because we are incrementing here, or string T because we are decrementing here? So once we traverse through the both strings, we can just basically check our frequency map that's containing only 26 elements and see if all the elements are 0. If they are, we know that the strings are anagrams, and if they are not, we know that the strings are not anagrams. So we will now code up the solution. We will first start by checking if the length of the string S and the length of the string T are the same. If they are not, we can just return false because there's no way, if they differ in length, that they are anagrams. They have to be the same length because if they are anagrams, then T is just a rearrangement of S, or S is just a rearrangement of T. Depends how you look at it. So next, we will declare our frequency map, which we will use to increment or decrement based on the occurrence of letter. Note that the length of the array is 26 because we are only using lowercase letters, but if the input contains some other Unicode characters, we could extend this to 128, or if it's an extended ASCII, we can extend it to 256 characters and then do the mapping like that. In that case, it will be still a constant space complexity because we are limited in the size when it comes to the frequency map. Next, we will traverse our both strings. We can use the length of each because they are, at this point, we are sure that they are the same length. We will get both charts first from the string S and then second from string T. And for the string current letter of the string S, we will increment the frequency map. And as you can see, we are using -a letter to get the corresponding index. So if the current letter is A minus A will be 0. If the current letter is B minus A will match to 1 because they are one place of difference in the ASCII table. And so on. C will match to 2 because C is just 2 places from A in the ASCII code table. Then we will decrement the corresponding index based on the letter that's appearing in the string T. After we traverse the strings, we will just traverse our frequency map, and as you can see here, we have a limited for loop, it just goes to 26, actually 25. 25 will be the last index we check. And for each of the elements, we just basically check if they are non-zero. If they are non-zero, we know that there is a mismatch between the frequency of letters in the string S and string T. So we return false because we know that they are anagrams. If not, we traverse the whole frequency map array. We can just return true because we know that they are anagrams. And that's it for today's video. I hope you liked it. Thank you.